Kia ora Year 12. This is question 3E from the school exam for integration this year, and here's the question here. So it's more obvious what you have to do in here, but it looks a little bit daunting. We're told we're dealing with a uniform solid right circular cylinder of blah, 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 blah. Okay, so reading through here, we've got a cylinder that's been chopped into 2 equal parts by a plane that passes through this line, and it makes an angle of 45 degrees with the horizontal. Right? But we're not sitting in a scholarship exam. We don't have to figure out how we can find that area. We're told the formula for the volume of the lower half of the cylinder is this. And then we're also given a hint about how to solve the integration problem with a substitution. So what we've got to do is make the substitution here and then just work through with this formula to show that that V formula, the volume formula, ends up giving us a cubed pi. So remember, when we do U substitution, we just need to be really careful to make sure that we've got everything in terms of theta instead of x. So the first thing I'm going to do is very systematically work through the substitution part. We're going to end up with a trig substitution, so we'll have to approach that quite carefully. And don't forget, we're going to change the limits of integration. Okay, so starting off from the start, we get let x equal a sine theta dx by d theta is equal to a cos theta. Right, I'm going to go very slowly through this question. So dx is equal to a cos theta d theta. Now let's look at what we've got to change inside the integral. Well, we've got to have dx, so we've got that covered. We need x plus a, so let's work that out here before we start mucking around with the integral. So x plus a is now a sine theta plus a. I might as well factorise that right now, so we get a sine theta plus 1. Okay, the 2 is going to stay as 2, thank goodness. And then the next thing is going to be a squared minus x squared. So this is the whole reason why we like these substitutions, because a squared minus x squared is equal to a squared minus a squared sine squared theta, which is a squared into 1 minus sine squared theta, which is a squared cos squared theta. So the square root of that, a squared minus x squared square rooted, will just equal a cos theta. Now the only thing we've got left to do is to work with the limits of integration. But I'm just going to highlight each of these things. This, and dx are all going to be replaced with what we've written out there. And it's really, really clear what we've done. So I think that's much better than doing it all with a v equals blah, blah, blah and getting into a big mess. Now the next step is to look at these limits. So we've got x equals a sine theta. And our current limits are from a to negative a. We want to change everything over to working with our variable being theta. So we're going to take this expression and say we need to have an expression for theta. So x over a is equal to sine theta. And we're going to take sine inverse of both sides. So sine inverse of x over a is equal to theta. So now that we've got that, we're finally ready to change the limits. So theta is going to equal, my top limit, sine inverse a over a, which is the angle whose sine is 1, which will be pi on 2. Right, let's give ourselves a bit more room. The bottom limit works in a similar way. Theta is equal to sine inverse of negative a over a, which is the angle whose sine is negative 1, which is negative pi on 2. Right, and if you're not liking that, just draw yourself a little baby sine curve. Here we go. We want sine, the angle whose sine is 1 is here, and negative 1 is down here. So finally we're ready to do a whole bunch of substitution, but because of the prep work we've done, it's not going to be too bad. I'm just going to go up to the top again to look at this expression here. So this is what we want to start out with. It's going to be the first thing that we write down. So we start with it in terms of x. And then we substitute everything in. New limits. X plus a. And here we've got the square root. I think I've already done this, but we've got a squared cos squared theta shown above. And then dx becomes cos theta, a cos theta d theta. Right, so this is what used to be dx. So I actually just made myself an extra step of work because I remember now that I have already said that this thing here was a cos theta. So that gives me 2a cubed cos squared theta times 1 plus sine theta d theta. Let's take out the constant, 2a cubed times this. Now, expanding out those brackets, we get cos squared theta plus sine theta cos squared theta. So we've still got a little bit of work left to do. Right, let's look at each of those integrals in turn. If you're watching this and you're in 13 MCA, this should be no problem from here. We've done these trig integrals lots and lots of times. We're going to use a double angle formula for this one. And when we look at the second one, we can see that we've got sine of theta here, which is linked up to the derivative of cos of theta. So the second derivative is very easy here. The cos squared theta one is going to go like this. Cos of 2 theta, which is easy to integrate, is equal to 2 cos squared theta minus 1. So cos 2 theta plus 1 is equal to 2 cos squared theta. Giving us, finally, cos squared of theta is equal to 1/2 plus 1/2 cos 2 theta. So we're going to take this and we're going to switch it over for this here. So just put that in a little bubble. There we go. This is not so elegant, but there we are. So down here, where are we up to? Well, we've got equals 2a cubed. I know most of you have stopped watching by now. Congratulations if you're still watching. Come and claim your chocolate bar. Right, so cos squared theta is 1/2 plus 1/2 cos 2 theta plus this thing here, which we can deal with easily. All right, and finally we're going to integrate. I'm going to get theta on 2. Let's see. Well, this is going to come from sine of 2 theta. That's going to generate a 2. We just want to have a 1/2, so it's going to be plus 1/4. This is going to be coming from something to do with cos cubed of theta. So when I differentiate cos cubed of theta, I'll get 3, -3, cos squared theta, sine theta. So this is backwards chain rule, and I need to have a -1/3 there. We've got pi on 2 here, -pi on 2 down here. So it's time to substitute some things in, but just let's note some values first. Sine of 2 pi on 2 is equal to 0, and cosine of pi on 2 is also equal to 0. There's my cosine curve. So you can see lots of stuff is going to fall out. So we've got 2a cubed times pi on 4 plus 1/4 sine of pi minus 1/3 cos of pi on 2 cubed. That's the first bit, minus -pi on 4 plus 1/4 sine of -pi minus 1/3 cos of -pi on 2 cubed. I'm sighing because this is kind of painful with the stylus. It's not nearly as painful with an ordinary pen. And there's stuff you could do in here with even and odd functions, right, to simplify, but we don't really need to worry. So we've got 2a cubed times pi on 4 plus 0 minus negative pi on 4. This is 0 plus 0 minus 0 again. Nearly there. Gives me 2a cubed times pi on 4 plus pi on 4. Remember, it's a show that, so don't jump too many steps. And finally, we get to the answer we want, a cubed pi as required. So there you go. Right, quite long. Sorry, that was 10 minutes and 45 seconds, but there were a lot of little steps in there. Leave me a comment or send me an email if you're stuck on any of it.